Hey everyone, Mr. Fritz here. We're going to talk about geometric applications of vector equations and lines in space. So let's dig right into this. First, let's talk about geometric applications of the r equals a plus tb vector equation. So remember, in this case, r is my resultant vector or my position vector. Here is like some initial point or point on the line, and then we have plus the direction vector or velocity vector b. So this kind of has some geometric applications. We're going to be intersecting lines together and finding points of intersection and all kinds of stuff like that. So in this example, I have a line with this vector equation. The position vector is given as this vector plus some scalar s times the direction vector 3, 2, and then line 2 is a similar vector equation with different initial points, different direction vectors. Note here that s and t are just some scalar values. They're not necessarily time in this case, right? So we're not talking about yachts moving or ships going across the water. These are just some scalar values. So, and that's because it's any scalar value, it can be in the positive direction, it can be in the negative direction. This just describes some line that's extending in an x direction and a y direction. And since these are different values, they're kind of extending at different rates. But we know what direction they're going in, and we know where they're starting. So I just want to point out that the s and t are different because of those reasons. These two lines, they meet at some point E. So, here's some line 1, and here's some line 2. Wherever they meet is at E. We want to use vector methods to find the coordinates of E. So basically what that means is we're looking for when line 1 equals line 2, when the position vector of line 1 equals the position vector of line 2. So what I can do is the position vector is written as the vector -2 plus 3s for the x, and then 1 plus 2s for the y. Basically what I did here is I took this vector equation and I just kind of scrunched it into one vector, and that's going to equal, this is L1, and let's go another color for L2. L2 is going to be red. And that is given as my second line, and that is 15 minus 4t and 5 plus t. So I want to know when those two vectors are equal, so I'm setting their position vectors equal. And what we can do is we can kind of drop the vector notation and just think of these as pure algebraic equations. So this is -2 plus 3s equals 15 minus 4t. That's kind of taking my x stuff here. And then let's take the y components. 1 plus 2s equals 5 plus t. Now let's do a little bit of algebraic rearranging, and let's move all the stuff to one side. Well, basically we have two variables and we have two equations. So if this is looking like a system of equations, it is. So I do a whole bunch of rearranging here, and I'm going to get, let's rearrange the top equation. And we'll rewrite that as, let's get everything to one side. That is a 3s plus 4t equals 17. And rearranging this bottom equation, I'll get a 2s minus t equals 4. So why don't I actually rewrite that stuff over here. 3s, I'm going to bring both of these up to here. 3s plus 4t equals 17, and 2s minus t equals 4. I'm going to solve this system using elimination. So I'm going to multiply this bottom equation by 4. So I will get 3s plus 4t equals 17, and then on the bottom I'll have 8s minus 4t equals 16. All right, now I add these up. The t's will cancel, and I get 11s equals 33, and that's convenient because s then will equal 3. Hooray! Well, what did we just find? What we found is the scalar value of s in my line 1 equation. Notice that I found s, I didn't find t. So I'm finding the scalar value of s where this line intersects this line. So I'm going to plug in 3 for s. to actually find that position vector, which will get me the actual coordinate for E. So let's do that. Line 1, the position vector, the xy is given by, here's my L1, and that's given by -2 plus 3s. That's the same thing over here, but let's do 3 times my s is 3. And then for my y, I've got 1 plus 2 times my s again is 3. So the position vector will be -2 plus 9, so that's 7, and then 1 plus 6, that's also 7. So the coordinate for E is the coordinate 7, 7. And there you go. There is where those two lines intersect. So why don't we do an example together? Now this one, I'm thinking that I didn't give you enough room on the notes for this. So I would grab a piece of paper if it's handy, because this is really going to be kind of labor intensive and a little bit repetitive, but this is good to practice finding where all these lines intersect. So I would pause the video if you need to grab a separate piece of paper, because I think you're going to need some extra room. I'm basically going to break this down into 4 parts. I've got all 3 of these lines, AB, BC, AC. Let's just kind of visualize what's going on here. So I have some point A, I have some point B, and I have some point C, and I've got lines AB, BC, and AC. And I know what the equations are of all of these lines, and I want to find where coordinates A and B and C are using vector methods. So that's basically what we did before. I have to find when these vectors are going to, the position vectors are going to equal the same thing. So let's kind of break this down into its parts. First, let's find point A. And the way I want to find point A is I want to figure out where the line AB will equal the line AC. So AB is going to equal AC. So what I'll do is, just like in the example before, I'm going to set the line AB 0 plus 2r and 2 plus r. That's given from this equation up here. That's going to equal AC, which is 0 plus t and then 5 minus t. All right, so now I can drop these vectors, and let's write this as a system of equations. So this is going to be 2r minus t equals 0, and this is going to be r plus t equals 3. Go ahead and pause the video if you're not sure where this came from. I just did a little bit of algebraic manipulation here. I'm going to add these equations up. So I get 3r equals 3, and then I get an r equals 1. So just like I did before, I just found an r value. I could go back and I could solve for t, but I don't really care about that. I'm just going to plug in r. Plug in 1 for r. And I'm going to go back to the equation that uses r, AB, and I'm going to find that actual position. So now let's plug it in. So AB, again, is given by 0 plus 2 times r, which is 1, and then 2 plus r, which is 1. And this is going to find me the position of coordinate A once I plug in 1 for r. So this is going to equal 2 and 3, which means that the coordinate for A actually is 2, 3. So that's one coordinate down. I just found this piece right here. So let's do the same thing now. Let's find the position, or the position of point B. So let's do B. To find the coordinate for B, I need to think about where the lines, let's do my ABC again, ABC. And I want when AB intersects with BC. So I want to know, when does AB equal BC? Well, once again, I'm going to take AB and I'm going to take BC, set them equal to each other. So I've got 0 plus 2r and 2 plus r equals, BC is 8 minus s and 6 minus 2s. Set these equations, the x components equal and the y components equal, so I get 0. Well, let's get rid of that 0. 2r plus s equals 8, and I have r plus 2s equals 4. All right, and now again, let's use elimination to solve this. So I'm going to multiply, let's multiply this bottom equation by a -2. So that's going to be -2r minus 4s equals -8. And this top equation will just carry over 2r plus s equals 8. Add them all up. R's cancel, and I get -3s equals 0. So s equals 0. So now I'm going to plug s in for this, this value right here for s. And that's kind of easy for me because that's just going to make this whole direction equal 0. So really this is like my initial point for this line BC. So the coordinate of B is 8, 6. All right, good. That's 2 coordinates down. Let's find coordinate C. Let's do this one in blue. So C is going to be the intersection of AC when that equals the line BC. This is going to find us coordinate C. All right, so once again, let's do the same thing we did before. 0 plus t, and then 5 minus t. This is my position vector for AC is going to equal BC, and BC is 8 minus s and 6 minus 2s. I want to know when these two are equal. So we'll drop the vector notation and go to our components or our parametrics. T is equal to 8 minus s, and 5 minus t is going to equal 6 minus 2s. And actually, let's rewrite this in standard form here. So we have t plus s equals 8, and we have negative t plus 2s equals 1. All right, let's add them up. And I get 3s equals 9, and hey, that's convenient. S equals 3. I'm going to plug in s, or plug in 3 for s right here. And let's find where coordinate C is. So coordinate C is going to be in the equation BC at s equals 3. So C is at, or is, too much. What I want to say here is that C is on BC at s equals 3, or when s equals 3, whatever you want to call it. So this is going to be 8 plus 3 times -1, and 6 plus 3 times -2. Plugging in s right here, and that's going to give me 8 minus 3, so this is going to equal 5. And this is going to be 6 plus -6, which is 0. So the coordinate C is 5, 0. All right, so putting that all together, we have an A is equal to 2, 3. We have a B that's equal to, or at the position 8, 6, and C at the position 5, 0. Whew, check for A. All right, let's do B. We want to know which sides of the two triangles are equal in lengths. So we want to find their lengths. Again, let's think about what we're dealing with. We have A, we have B, and we have C. So here's my lines connecting all these coordinates. And now what I want to do is I want to find the lengths of these lines. So I have to kind of think about what vector AB is. I have to think about what vector BC is. I have to think about what vector AC is. And so let's do that. Let's find vector AB first, and that's going to be given as I have to subtract B by A. So let's take my coordinate from B. Let me jot down those 3 coordinates. A was 2, 3. B was 8, 6. And C was 5, 0. So if I want to find vector AB, I have to take B and subtract A. So that's going to be 8 minus 2 and 6 minus 3. So this vector is going to be 6, 3. That's vector AB. Let's next do vector BC. That's going to be subtracting the coordinate C from the coordinate B. Coordinate C by the coordinate B. So 5 minus 8, and then 0 minus 6. So that's going to be vector -3, -6. And then finally we have vector CA, or AC, doesn't really matter. Let's do CA. And that's going to be equal to A minus C. So 2 minus 5 and 3 minus 0. So that vector is equal to -3, 3. All right, and right off the bat, I'm looking at these three vectors. I'm seeing these two as being the same in magnitude. And that's because I still have these same two components. Yeah, they're in different orders, and yeah, they have different signs, but still I have a size 6 and a size 3 and a size 6 and a size 3. Those two, the magnitude, let's go one more color here. Let's go purple. The magnitude of vector AB is going to equal the magnitude of vector BC. And hopefully you can kind of see why I'm saying that's so apparent. The components are all the same size. So let's find what the actual magnitude is. That's the square root of 6 squared plus 3 squared, which is equal to the square root of 36 plus 9, so 45. That is the lengths of AB and BC, which are equal in magnitude. Check. All right, that was a whole lot of work. But again, we really did the same thing kind of over and over and over again. So I want you to try this U-try problem. This has a whole lot of parts to it. We've got 4 parts to this and a lot of finding these intersection points. But give this problem a shot. It's going to take you some time, and again, you'll probably need some extra room. So pause the video and come back when you're ready to check your answer. All right, and here is my answer for this U-try problem. They're all down here, quite a few pieces of information to take a look at. If you had some trouble with this, I will be posting a video in a little bit about how to actually go through this problem if you need another walkthrough. But if you were able to get there, good for you. Let's take a break for this video, and then the next problem, we're going to do another example where we're kind of diving deeper into these geometric applications.